I'm Professor Rad, and this is Precalc video 218, Exponential Definitions and Laws. In this video, we'll be defining exponential functions and looking at some laws or some properties of exponents. So let's get started. As a reminder, these are some of our laws for exponents. So whenever we have laws or properties, we want to be stating what the different variables we're using are allowed to be. So they'll usually have like a let statement here, like this one. So we're going to let A, B, X, and Y be real numbers. So that means these can be any decimal, positive or negative, except A and B have to be greater than 0. And then all of these properties follow from that. So if I have A to a power times A to a power, I can add the powers together. So for example, for this first property, if I have 3 to the 5th, and I multiply that by 3 squared, that would be the same as 3 to the 7th. For the second property, if I have A to the X and I raise that to a power, that's the same as if I multiply the powers together. So for example, if I have 3 to the 5th and I square that, then I'm going to get 3 to the 10th. Number 3, we have if I have a product to a power, that's the same as if I took each of those factors, raised it to a power, and then multiplied them. So for example, if I have 3 times 5 and I square that, that's the same as 3 squared times 5 squared. Number 4 is pretty self-explanatory. 1 to any power is 1. So if you have 1 to the 3, 1 cubed, it'll be 1. This is because exponents are repeated multiplication, and if you multiply 1 by itself, however many times, you're going to get 1. Number 5 is our property for negative exponents. So if you have a to the negative x, that's the same as 1 over a to the x, or the fraction 1 over a to the x power. So for example, if I have 3 to the negative 2, I could think of that as 1 over 3 squared, or I could think of that as 1/3 being squared. And lastly, any number to the 0 power is going to give us 1, except for 0. Okay, this was up here. This is why we were not equal to 0. We needed to make sure we were greater than. So if you have 0 to the 0 power, that's going to be undefined. So these should all be fairly reviewed, pretty review topics from previous algebra courses, but we're going to be applying these and using these to simplify exponential functions. So just wanted to go through the list and quickly review them. So now let's go ahead and define an exponential function. And just like we did with polynomials, remember with polynomials, we had leading coefficients and terms and all like different components of it. We'll do the same thing for exponential functions. So we'll talk about all the different components that go into making an exponential function. Here's our definition for an exponential function. So an exponential function is a function that has the form c times a to the x. When we're using these variables, c is non-zero, because otherwise we would just have f of x equals 0, which is a constant function. We want a to be greater than 0 so that we can apply all those nice exponent properties or laws we just talked about. And we want a not to be 1, since 1 to any power is just going to give us 1. So we would end up with f of x equaling c, which would be a constant function. In this case, we're going to call c the initial value, and we call a the growth factor. So for an example, if I have the function f of x equals -2 times 5 to the x, in this case, -2 is c, so -2 is the initial value. And since we have 5 to the x, 5 is going to be called the growth factor. Now, you might be wondering why these terms are the terms that were being used, right? So why do we call it the initial value and why do we call it the growth factor? So we're going to do a little experiment with this function f of x to see where those terms might come from. So for example, if I want to find f of 0, I would get -2 times 5 to the 0. Well, 5 to the 0 is 1, so we get -2. So the reason that this -2 in the front is called the initial value is because oftentimes when you start an experiment, you're starting your time at mark 0. So at the beginning, at the initial time of the experiment, we get that number because anything to the 0 will give us 1. So that's where that term comes from. As for the growth factor, let's continue. So let's find f of 1. So f of 1 is going to be -2 times 5 to the first. And that's the same. I'm going to write it this way for particular reasons, but that's the same as -2 times 5. Now, if I look at this, I notice that -2 was the answer that we got when we did f of 0. So if I wanted to, I could rewrite this as f of 0 times 5. So if I want to find f of 1, one way that I could do that is I could take f of 0, the previous y value, and multiply it by 5. When I find f of 2, that's going to be -2 times 5 squared. And I'm going to use the associative property to regroup this a little bit. 5 squared is 5 times 5. So I'm going to write this as -2 times 5 times 5. Right? We would get the same thing whether we evaluated this expression or this one. The reason I wanted to write it this way is because -2 times 5, well, that was what we got for f of 1. So we could write f of 2 as f of 1 times 5. Right? So f of 2 can be found by taking the previous value for y and multiplying it by 5. And this is going to be the case as we move forward, as we continue. So if I have f of 3, that will be -2 times 5 cubed. But that's the same as -2 times 5 squared times 5. Right? Again, I'm just basically factoring out one of these 5s to be by itself. And -2 times 5 squared, why, that's what we got when we initially substituted into f of 2. So this is f of 2 times 5. So if we were to continue this in general, if I wanted to find f of n, I could just take f of n minus 1 and multiply it by 5. In order to get, like the next y value, if I increase my x's by 1, I'm going to multiply by 5. This is where the term growth factor comes from. So remember, factors are things that you multiply together to get a result. So what the growth factor is saying is that we're going to grow by a factor of 5 for each increase in value of 1 for x. So we multiply by 5, since 5 is the factor, each time we increase our x value by 1. What this does is this gives us a nice way to be able to distinguish between a linear function and an exponential function if we look at a table of values. So let's take a look at that. For this example, we're going to look at these two different tables. We have one for f of x and we have another table for g of x. And we're going to determine whether each of these functions is a linear function or an exponential function. So a linear function is going to increase by its slope, and an exponential function is going to increase by its growth factor. I said increase, but could be increase or decrease, right? So if you think about what happens with a line, when you think about your slope is your y value might go, say, up 5 over 1, up 5 over 1, and so on. So if I have one y value, in order to find the next one, I add that 5. Then to find the next one, I add 5 to go up, or whatever your slope is, right? If your slope is 2/3, you could think of it like going up 2/3 over 1, up 2/3 over 1, right? So when you have a linear function, what you'll see in the table is it will either increase or decrease by adding the same amount each time. When you have an exponential function, as we just saw, it's going to increase or decrease by multiplying by the same thing each time. So let's check these out. If I look at this first function here, f of x, and I want to think about how I can get from 7 to 4, probably one easy way to get there is to subtract 3. So I can go from 7 to 4 by subtracting 3. Let's see if this pattern, if this subtracting of 3 is going to hold for each of these pieces. So to go from 4 to 1, yeah, I can subtract 3. To go from 1 to -2, I'm subtracting 3. And to go from -2 to -5, I'm subtracting 3. So each time when I start at one y value, to get to the next one, I just subtract 3. This is an indication of a linear function because that subtracting 3 is your slope. So our slope is that -3 because that's how much we go down each time we move over 1. For writing an equation of a function, for a linear function, if we know the slope and the y-intercept, we can write the equation. So fortunately, one of our x values here is a 0. So this is telling our y-intercept is 4. So the equation for f of x is going to be -3x plus 4. All right, now let's take a look at g of x and see if it follows the same or different kind of pattern. So for example, if I go from 64 to 16, oh gosh, that's going to be what, 48, right? So if I do 64 minus 16, that would be a difference of 48. If I go from 16 to 4, that's going to be a difference of 12. And then from 4 to 1, that's a difference of 3. So you see how each time we go down this list here, we're no longer subtracting the same amount. It changes every time. So that means this function that's being represented here is not linear because it doesn't have a constant slope. So let's see if we can find a new pattern. So rather than trying to identify something we are adding or subtracting, let's see if we can multiply or divide by the same value. So for example, if I wanted to get from 64 to 16, if I divide 64 by 4, I will get 16. My cat is approving of this math here. So we want to be able to express this in terms of multiplication. So I'm going to write multiplied by 1/4. If you divide by 4, that's the same as multiplying by 1/4. So let's see if that is going to be the case for each of these now. So if I do 16 and I want to get to 4, I could multiply 16 by 1/4 and that would give me 4. So going from 16 to 4, I can multiply by 1/4. And this is going to continue. If I multiply 4 by 1/4, that will give me 1. And if I multiply 1 by 1/4, that will give me 1/4. So this time, rather than add or subtract the same amount each time, here we're going to be multiplying by 1/4 each time. So that means this is an exponential function. And just as the amount we subtracted told us the slope, the amount you're multiplying by is going to tell you your growth factor. So A is going to be 1/4. Also, similarly, just as the y-intercept told you the y-intercept here, in this case, this y-intercept is going to tell us our initial value. So here, C is going to be 16. So if I think about my exponential function form, y equals c times a to the x, then g of x, in this case, will be equal to 16 times 1/4 to the x power. Now, Lenny over here, apparently, is not happy having a base of 1/4. He wants to have a whole number or a whole number base. So we can do that by using the properties with that negative exponent. So I could rewrite this as 16 times 4 to the negative x. That would be another way of writing a formula for the function. All right, that's going to be it for this video on an introduction to exponential functions. In our next video, we're going to look at some basic exponential equations and see if we can solve those, what techniques will be useful. So I hope this helped. And oh, Lenny is purring now, probably because it's the end of a math video. So I hope this helped, and I'll see you in the next one. Bye for now.